parte, non vedo. Impazzito. Vedi, non potrei modalità relatore. Dov'è la presentazione? Dove? Si vede. No, visualizzazione relatore.
We can say it.
Non va avanti. Ok.
Doctor,
Can
you're
you see my
not
presentation?
audible.
Can you see my presentation?
Yes, yes, now it's clear. Please go ahead.
Okay, thank you. I'm very sorry for the interruption. I'm
It's
Dr.
o-
Vincenzo Entamaro,
Okay.
and
clear.
this is my presentation regarding the AI application of healthcare. You will see different application of AI in healthcare. Actually, this is my slide regarding my life. I also have a company which does indoor positioning and so on. You can see my company on the left, which is called Next to Me. I also mainly work in computer vision, and we work with the military too. And these are my kids, so very busy life. Let's go straight to the point. So gait analysis. Now I will talk to you about gait analysis for neurodegenerative disease assessment. So how you can see here, there is this actor which is pretending to perform various pathologic gait, such as hemiplegic gait, diplegic gait, the myopathic gait, the neuropathic gait, the ataxic gait, and the Parkinsonian gait. The point is, how can we teach the machine to learn pathologic gait in order to understand, to let the machine to understand if there is a neurodegenerative disease or not? Well, our answer to this problem is I will show you some technologies that we have developed as a team during this during my research career. And first, we used a pose estimation algorithm such as OpenPose. You can see it on the left. It's a pose estimation algorithm which extracts the body joints coordinates in time from the video of the person moving. On this, you can see which is trying to perform a sit to stand test, 5 times sit to stand test. And on the right, you see the extracted body joints coordinates in time. As you can see, there are minor errors because there is not always, not every time all the coordinates are taken. Not only, there is also the projection of the nurse in the mirror, which causes problem. So we have to to face all these problematics. First of all, I want to introduce you the model that we used, which is called the sigma log normal model. And in order to describe the patterns of a neurodegenerative disease, gait in this case, or the sit to stand, in addition to standard features that could be extracted, such as the velocity, the displacement, the acceleration of all the body joints coordinates, we also used the kinematic theory of the rapid human movements and its sigma log normal model. The sigma log normal model, which is expressed by the formula that you see there, was developed by Réjean Plamondon, and it is based on the idea that a rapid human movement can be represented as a sequence of overlapping strokes, where each stroke is driven by a log normal impulse response. In other words, the model suggests that the movement of the hand, of the wrist, of the legs, and so on, is controlled by a series of motor commands, with each command generating a basic impulse that follows a log normal shape in time. So the log normal impulse response is characterized by the two parameters, amplitude A and duration D, but also the sigma log normal model introduces two additional parameters, such as the time delay t with 0 and the standard deviation, the sigma. Those four parameters, the amplitude, the duration, the time delay, and the standard deviation, define the shape, the amplitude, the time shifting of each log normal impulse in the response. So the kinematic theory of rapid human movement was developed by Plamondon and in the 90s, first 90s, and the model can be successfully applied, has been successfully applied to reconstruct the original signal of a movement, starting from, data points. So here you can see in the slide, on the left, the pose estimation of the nose movement pattern of a healthy person on the left, and on the right, the nose movement pattern of a person with Parkinson. Okay, so what can we say? We can observe that the person with Parkinson has strong peaks and lots of little vibrations in betweens. If we see the noise through signal to noise ratio, or just from the plots, the overlapping of the in black, there is the numerical, so the data points that arrive from the sensors, in this case from the pose estimation, and in blue there is the reconstructed signal from the sigma log normal model. We can say that the kinematic theory of rapid human movement and the sigma log normal model is capable of capturing fine-grained movements, even the little vibrations of the Parkinson disease. So after gathering this model and applying this model, we have, first of all, collected a data set containing 115 videos of 40 subjects divided in patients and control healthy subject, 20 healthy people and 20 patients with different neurodegenerative diseases and different severity levels. 21 subjects were female and 19 are male. So at the end, 61 videos of healthy subjects and 54 videos of patients. Then we used this classification pipeline. So we performed fisheye removal because the video had bottle-like shape. Subject selection, we selected the patient, and so the body, I mean, the only the body joints coordinates of that person were analyzed. Then we performed pose estimation. We performed the missing outlier coordinate adjustment, step segmentation, step coordinate smoothing with the Kalman filter, and feature extraction. And then we used the interpatient separation scheme to extract in the interpatient separation scheme, we used extracted feature of some people, steps for training, and extracted feature of completely other people, steps for the testing. And this separation scheme ensured that there is no information of some people in the training, of the same people in the training and the testing set. So there is no blooding of the information, and is very suitable for medical purposes. So we use the five different classification algorithms, such as the k-nearest neighbor, the random forest, ADABU, support vector machine, SVM with linear RBF kernel, and tenfold cross validation with interpolation separation scheme. And we reached the 95.5% of accuracy using the linear SVM in binary classification problem. So discriminating healthy people from people with some form of neurodegenerative disease. This is the feature ranking. As we can see, actually, it's very difficult to see, but at the last one is the D command of the sigma-normal model. When we deepened in the analysis, we were capable of understanding that really this kind of feature was capable of finding correctly people in early neurodegenerative disease, in the early stage of the disease. So the sigma-normal model was significant because added the early detection of the neurodegenerative disease. These are a few publications that we did on this topic. Then I used on the same problem the neural networks. So I have invented the multi-speed transformer network for the neurodegenerative disease assessment and also activity recognition. Let's go directly to the, to the architecture. The intuition behind this architecture actually is the capability of the deep learning of learning meaningful time-dependent correlations and patterns at two scale levels, fast and slow. Multi-speed transformer is in fact composed of two parallel branches. You can imagine similar to a slide viewed by a microscope. At the high resolution, it's possible to observe very detailed features, for example, cells. And at lower resolution, it's possible to observe more broad concepts. In this specific case, the fast branch, the lower branch, is capable of finding broad concept, which means long-term patterns, such as, for example, the freezing gait in Parkinson's disease. While the slow branch, the upper branch, is capable of finding fine-grained movement in the fine-grained movement, such as the tremors in the Parkinson's disease. By merging both findings, the network learns to correlate the presence of specific patterns in the fast branch, such as the freezing gait, with the presence of specific patterns in the slow branch, such as the tremors. Actually, we can say that for example, the fast branch, the lower branch, is composed by monodimensional convolution with strides of 3, followed by another monodimensional convolution with strides with dilation rates 2, positional encoding, multi-headed attention. The residual is then connected, layer normalization, and then it's concatenated with the upper branch. The upper branch is slower because it has a monodimensional convolution with strides of 1, and followed by a monodimensional convolution with the dilation rates of 2, positional encoding, multi-headed attention, residual, and then normalization and concatenation with the lower branch. And then it follows a standard feed-forward architecture. The results are very significant because the multi-speed transformer in the binary classification, healthy, non-healthy, reached 96.9% of accuracy, which is over 1% higher with respect to the linear SVM that we saw previously. And it also outperformed the vanilla transformer and also temporal convolution TCN, the temporal convolution network. These are instead the results on the multi-class classification, but only in the initial stages of the disease. So healthy control subject and the initial stage and mild stage. we reached the 71.6% of accuracy and the 73.9 of area under the rock, outperforming all others architectures, of course, and the shallow learning techniques too. This is the publication, just in case you want to read and deepen more. Then I also worked on fall detection. Fall detection is very similar to what we performed for the first gate classification. In this case, we used the two datasets, the LE2I dataset, which contains 192 fall videos and 57 non-fall videos, and also the URFD dataset containing 70 videos in total, 30 falls, 40 activities of daily living. Okay, go on. Okay, it seems to be blocked. Okay, it's not going to the next slide, sorry. Let's fix it. Okay. Sorry, got a problem. Crashed. I'm trying. Very sorry. Okay. I'm going to the right slide. Never had so many problems with PowerPoint like today. I'm very sorry for that. Okay. Can you see it?
Yes.
Thank you. So, hoping it continues well. We performed the pose estimation for fall detection. This is the pipeline. The pipeline that we use is the same pipeline as gate, so I won't explain it again. We used the sigma log normal model as before. So I already explained what is the kinematic theory of rapid U and movement. In this case, there is also the velocity profile of the nose of a person non-falling on the left and a person falling on the right. It's clear that we can see a clear pattern when the person is falling as on the right. And this is the accuracy that we reached. On the LE2I dataset, we reached the 98% of accuracy in exactly the same condition as others. And on the URFD dataset, the 99% of accuracy. If you want to deepen more, this is the publication that we wrote. Then we also worked on Parkinson recognition via audio. So the dataset that we used contains synthesized repetition of sustained vowels A and I Each vowel had been recorded at least twice for a total of 1,011 recordings. The dataset is broken down into training and testing datasets with always the interpatient separation scheme. And then we also balanced the dataset because there was a strong imbalance between the classes. So we performed the classification and we used shallow learning and deep learning. So for deep learning, we generated MEL spectrogram images out of the different audios. And then we used the standard deep learning techniques such as ResNet 15, Inception ResNet, and DenseNet. And for shallow learning, we used the MEL frequency central substrum features, and then we perform the classification with SVM, a random forest, and KNN. And you can see here the results, and clearly the ResNet 50 is outperforming all other architecture as well as shallow learning techniques. Then we also started working during the pandemic on the COVID-19 recognition via audio. So we developed a pre-screening technique which is capable of finding the presence of COVID only from cough and breath sounds by using a normal smartphone. And we have developed this architecture which is called the auditory cortex ResNet, which is a biological inspired deep neural network, which is especially designed for sound classification. Our ResNet has been demonstrated to provide the state-of-the-art results on various COVID-19 cough and breath classification tasks. And in addition, its generalization powers is also demonstrated in cross-dataset test. We also say out-of-distribution tests, both on COVID-19 cough and breath sounds, which means that it has been trained on a dataset called COSVARA, which was a very big dataset from India, and it has been tested on the Cambridge cough and breath sound dataset, which we obtained from the University of Cambridge, showing the robustness to biases. So this is the architecture. With this architecture, I won the Huawei University Challenge in December 2021 in the Edge AI category. It is built on the intuition that mammals have evolved the sound perception in order to focus on certain frequencies better than others frequencies that are not audible to the human ear, even with a phonoendoscope. This intuition is encoded by the presence of three attention mechanisms, namely the squeeze and excitation mechanism, the convolutional block attention module, and the novel one that I invented, sinusoidal learnable attention. This last attention mechanism, which is composed, is the big gray area that you can see here, let's say, act like a hypothetical biological grandmother neuron because it merges relevant information from the activation maps at various levels of the network, acting similarly to a biological pyramidal-like neuronal cell that have been reported by a neuroscientist to code for, let's say, high-level concepts. OCRSNet takes as input raw audio and outputs the class healthy, non-healthy, and even multi-class. Without any kind of preprocessing on the audio, data augmentation is not required, data augmentation or manual spectrogram generation, because the model includes elements that are also present in the biological auditory cortex of mammals, such as rats, as you can see in the picture on the left. And here are some similarities. It is composed by 6 main blocks, as you can see on the left. It can evolve sound perception because also the MEL spectrogram layer is trainable, which means that the gradient descent removes the irrelevant frequencies and keeps the frequencies that are useful for the task. Actually, when we do the Fourier transform and then we apply the MEL spectrogram, MEL filter bank, the bank of the filter are trainable, which means that this was developed in TensorFlow. So TensorFlow during the back propagation can change these values and thus suppress frequencies that are not important and leave only the frequencies that are important. It has many attention levels, and the number of neurons within each stage has similar proportion to the neurons found in rats. Here, there are the accuracies that we reached. We can say that this is the out of distribution, the cross dataset test results. And we can say that we reached the 70.98% of accuracy, let's say F1 score, and the 81.86 of area under the rock curve in cross dataset testing, training on Cosvara and testing on Cambridge. So really out of distribution test on these massive datasets. If you want to deepen more about this architecture, I suggest you to read our publication, AucuResNet on pattern recognition. And that's all. Thank you. I'm very sorry for all the problems of PowerPoint today. Really. If you have questions, I'm ready to answer your question.
Hi, Dr. Tamaro. I don't know if you can hear me. This is Dr. Tiberido from MD Anderson. How are you?
Thank you.
Can you hear
Welcome.
me? Yes. I enjoyed your presentation. How can you distinguish, for instance, that the cough is associated with COVID-19 and not any other causes? Because I think it's very difficult to distinguish what the symptom is associated with, because cough can be caused by many causes.
I agree with your question. And in fact,
how do you differentiate, that this is COVID-19 related versus, cough from pneumonia, from another other source, from bacteria or from cancer, or, simply an allergic reaction? Is there something specific in the cough that you identified and associated with COVID-19?
Yes, and in fact, I can answer you with two things. First, the data set. Those data sets that we used in cross data set testing were massive. So especially the Cosvara data set, which we used for training, contained people with cough and other kind of diseases like BPCO, sorry, say it in Italian, COPD, the chronic obstructive pulmonary disease, and other kind of conditions, but they were identified as healthy from the COVID perspective, So
non-COVID, in other words.
Exactly.
So it's not just the COVID, but it's, cough associated with perhaps a test that was positive for COVID versus cough from other conditions, right?
Exactly. Sort of. In fact, all people in both the data sets, we selected those data sets because they were very, very well done at the time, because we started our research in 2021, 2020, at the beginning of the COVID pandemic, and then it was published in pattern recognition in 2022. So 1 year of, reviewing it takes time, but the point is that at the time there were those two big data sets that were very good, because they ensured that people with COVID were screened with a PCR test.
Correct.
So other people that had other kind of diseases, but a clean PCR test for COVID, they were in the data set too. So to answer your question, we have developed another, and it's currently under review, technique, an explainable AI technique, which concretely and says what is the part of the audio, the only signal that is discriminative of the COVID condition. And when we removed all the frequencies that were not important to the network, we understood by using this technique that we are publishing right now, which is an explainable AI technique new. It's a theorem, by the way, because if we apply LIME on spectrogram images or GradCam, it won't work, because those are frequencies, not images, not RGB images. So it won't work because there are preconditions different. The preconditions are different. And we want to be sure that the frequencies used for COVID are just the most important frequencies, also important for the network. So when we rebuilt the audio of only the most important frequencies, then we understood that is the mucus on the top initial level. I mean, I'm not a medical doctor, but at the initial part of the lung, because the pneumonia is inside the lung. Instead, the COVID, it's a sound that is generated, let me say, here. Okay? And when we went through, in the paper, there is also Luigi Moretti. The father is the pneumologist. When we went through the father and said, oh, listen, we have discovered it. How do you listen for COVID-19? He said, oh, when he heard it, he said, oh, yes, that's the sound I'm searching for, which is between a crackle and a whistle, but happens here in the top lung. That's it.
I see. Okay, so it's the location also you're looking at, and the characteristics of the sound.
He can hear the sound because by removing all the not important frequencies and leaving only the most important frequencies, and then rebuilding the sound with the computing the pre-image in output, the physician had the sound.
Great, thank you.
You're welcome. Thank you for the question. Very appreciated. And also, any other question? Okay, so I